Welcome everyone. So this is our 108th live stream geometry. We have 3 people here with us now, and today I'm going to take problems from a couple different mock contests around the world. Actually, I take that back. It's just one mock contest. It's the AoPS Quarantine Geometry Olympiad. So this was in 2020. I don't know if I've already done this on my channel or not. I've been recycling a couple problems, but I don't remember these problems or their solutions. So if you'd like to join us in the future, feel free to email me at mgreenb801@gmail.com. We meet every Sunday at 8 a.m. U.S. Central Time. All right, so I'll share my screen. Here is the first problem. We have a lot of people joining so far. So can you guys all see my screen?
Yes.
Okay. So this is the first problem. It's a little bit easier, but the others start to get harder. So let's see. We have ABC, and then we have a line L. I'm just going to draw D and E. So maybe something like that. P and Q are the midpoints of C, D, and DE. Okay. And so this should be P and Q. P, Q. The lines through P and Q perpendicular to L. So we try to see where do they meet the perpendicular bisectors of AC and AB. So AC and AB at M and N, and we want to show MN is parallel to PQ. Okay. How do I make it a nice diagram? Line through P perpendicular to L, and we want to see where it meets this bisect. So yeah, I'm going to want to draw the midpoints of AC and AB, but first I'm going to draw the points. So a line through P, and then this line, we let this meet at N. Okay. Let's draw the midpoints of these sides, F and G, and the circumcenter should be where they intersect, so that should be O. All right, and now I will make it look nicer. So yeah, once I add the tools, yeah, there's probably a way to draw this faster, but for the time being, this will do. Okay. All right. Let's expand this a little bit. N and G are a little close together, so let's first draw the lines. So we have this, we have this, so we have PH, and then we have the lines through P and Q perpendicular. Did I draw this right? Maybe I did. So P and Q are the, I need B, E, and CD. Yeah, I guess this is the whole picture, right? I just want to make N and G look farther away, but it's not that easy to do that. Oh, but you can move around D and E, so that makes things a lot easier. Okay. Maybe something like that. So M and N are where it meets the 2 perpendicular bisectors, and we want to show MN is parallel to PQ. Okay. This almost looks a little bit like the Gauss line, because you have the midpoint of this, the midpoint of this. I don't know if it's worth drawing the other midpoint, but it would pass through that. So I'm just going to do it just in case it's useful. So we know that P, Q, and J are collinear. But I already drew it. We just need to draw this. All right.
We need to show that NQPM is a parallelogram, so it is sufficient to show QN is equal to PM.
Okay. Oh, but yeah, because these two are both parallel. That's a good point. All right. So yeah, we have to show that this is a parallelogram. I could draw this point too if I really want, but it's getting a little crowded. Maybe that looks okay. And looks like Amal just joined. Okay. Let's see. Hello. Yes. So we have triangle ABC, and then we have we have B and E are like any points on AB and AC. So we have a line that cuts it at D and E, and then we draw the midpoints of BE and CD. So those are P and Q, and we draw perpendiculars to line BE, and we see where it meets the two perpendicular bisectors of AB and AC. So we say it meets them at M and N, and then we want to show MN is parallel to PQ. All right. So we have a couple cyclic quads, right? We have this, and probably one more. What am I missing? Let's see. So this is a right angle and this is a right angle. So does that make a cyclic quad somewhere? This one right here. Yeah, I'm not sure how useful this Gauss line is. Interesting.
We have that angle PFM is equal to QGN.
PFM is equal to QGN.
Yeah, and that is an angle chase. You could just notice that PF is
These are midpoints.
parallel to AD. Yeah, it is the mid.
Interesting. I
this
wonder
is nice, since we want to show now that the circumcircles of FPM and QGN are the same size.
Okay. That would solve it. So FPM and QGN, if we can show they're the same size, then that means NQ equals PM. And then that solves the problem because they're parallel. That makes sense. So yeah, FP and QG both pass through the midpoint of BC. And I'm going to hide this. I don't think it's that useful anymore.
We can now maybe try a bit of a trig.
Okay.
Since the radius of circumcircle, for example, of G and Q, that would be like GQ over sine G and Q.
Okay.
Or 2 times the radius, but it doesn't matter really. It's just like that. So GQ is something we kind of know. It is just a half of AE.
Oh, okay.
And that angle G and Q also looks pretty nice. I mean, that is just like 90 degrees. It is just like the angle between lines QN and OG, and that is like something we know since GN is just QN is just perpendicular to DE.
Yes.
What
Yeah.
I say is I think we just kind of have to compute a bit of things and that's it. But nothing is hard.
Okay. So yeah, so this is the angle between GO and NQ, and NQ is perpendicular to DE. So NQ is perpendicular to DE, GO is perpendicular to AB. So if we have two perpendiculars, it would, I mean, it would be 180 minus angle ADE, right? So
Oh yeah. So this is just the solve, because yeah, you will just have it solves itself.
So angle GNQ, yeah, is 180 minus ADE. And then we have the same thing for FMP. Angle FMP is 180 minus AED. And yeah, then it's just a law of sines, and that finishes it. All right, so I'm going to write that up. The next problem, I'll do the problem from Serbia next. Okay, so all right, so let's do this. So I'll just say label the points as shown. Just so I don't have to write it all out. I guess we don't even need point L, do we? Probably not, right? Just figure I might as well make the picture as simple as possible. Okay, so GQ, I guess it's not that obvious, so first I'll write out the proof and then maybe I'll finish up the labeling then. So triangle GNQ, GQ equals half AE. GQ is equal to AE over 2. And then we have sine GNQ over GQ. Or I'll say GQ over sine of GNQ is equal to GQ over sine GDK. Which is GQ over sine of ADE. well, let me write it out like this. So I'll say let R of Gn, let R be the radius of, I'll say R1. Radius of GQ. So this would be 4R1. I think this would be 4R1, right? I think that's the formula, right? So GQ, and then this is equal to AE over 2 sine ADE. All right. And
I think it's 2R1 instead of 4.
2R1? Okay. All right. And then so similarly, let R2 be the radius of FMP. Then 2R2 is equal to AF over 2 sine of AEB, which is equal to AE over 2 sine ADE, is equal to 2R1. And that means that R1 equals R2, which means that and then that means that NQ equals MP. Is that right?
Just have to write the angle trace for which proves the two angles are the same.
Okay, so that angle NGQ equals angle MFP, right?
Yes.
Okay, so the angle between that and that, and then AD over 2, not AF over 2. Oh, you're right. AD. If I even do it, I might have switched these, right? Maybe this should be, oh no, it is, yeah, D. Okay. And then the angle between GN and GQ is the angle between AB and BE. GN and GQ is the angle between AB and BE. Is that right? I'm not so sure if that's right. So GN is perpendicular to AB, GQ is perpendicular to BE. So yeah, that would be angle ABE. And then this would be the angle between AC. This would be ACD, but those two angles aren't necessarily equal. So what did I do here? EM and GQ.
So MFB is the same as ACD, right?
Yeah.
And both of them are 90 minus A, so we are done.
But these CD and
Okay,
BE aren't, they're not altitudes. So BE and CD don't have to be altitudes. Which is why I'm confused here. So yeah, maybe I'm missing something.
You made a mistake. Like it's not A, B,
AD
E.
are arbitrary, right? Now is
Oh, it's A, B, and D, E. That's what it is. Okay. Yeah. So this is and this is the angle between FM and FP.
I don't think that's true either.
That's not true either. So
And GQ, it is very easy. It is just 90 minus angle A.
this angle NGQ
BAC.
90.
BGN is 90 and BGQ is angle A since GQ is parallel to AE.
Oh, so angle NGQ. Yeah, that's a much better way to do it. Angle NGQ is 90 minus angle BGQ, which is 90 minus angle A. That must be what Anmo was trying to say. Yeah, I missed it. Which is 90 minus angle PFC, which is angle MFP. And so that means that together these imply that NQ equals MP. P. And then NP is parallel to NQ since both are perpendicular to NP, so then we have a parallelogram. To DE, and that implies MPQ1 is a parallelogram. And that implies MN is parallel to PQ. All right. So it took me a while to write that up, but yeah, not too bad of a problem. All right, so let's move on to the next one. Let's see. So this problem Stefan showed me. So he solved this one on the exam. So now we'll see if we can solve it. Let me see who's still on. Oh, looks like Serdar hopped off. Okay, so we have a triangle ABC. I is the incenter, and omega is the circumcircle. There we go. And its tangent at D. And then we draw this. So yeah, whenever you see the perpendicular to I at AI, it makes you think of the Mixtilinear incircle. So E and F are where it hits A, B, and AC. And then we draw the circle AEF, and it meets omega and AI at G and H. And H should be the center of the Mixtilinear incircle. So this will be G, this will be H, and then we could draw the Mixtilinear incircle. And let's see, the tangent at G to the big circle meets BC at a point J, and AJ meets the circle at K, the big circle. So I'll draw this better in just a second. So this is K. And then DJK, we want to show as tangent to GIH. Okay. So we have, let's draw it, DJK and GIH. And yeah, it's pretty easy to see from this picture. So I'll admit I already saw this before, but it's pretty easy to see that point their tangent at is the Mixtilinear Incircle. So obviously GeoGebra makes that easier. On a test, you probably wouldn't be able to use GeoGebra, but we have GeoGebra now, so we can see it. All right. Let me draw the midpoint of the arc just in case it's helpful. All right. Yeah. So first of all, we want to show that JKDL is actually cyclic and that GIHL is cyclic, and then we want to show their tangent.
4 concurrent circles remind me of complete quadrilateral, right?
Complete quadrilateral.
Yeah, L should be Michael point of something.
M is the McKell point of something?
L because
Oh,
4 circles concur at L, right?
oh yeah, that's true. One sec, I'll be right back. Sorry. All right, I'm back. Thanks for waiting. So yeah, maybe it's a McKell point. I think I noticed something else too. So this problem looks a little bit like the Sharky Devil configuration. So let's see. We draw these 2 points. Okay, maybe that's not so useful. But yeah, I'm still going to draw these 2 points. I wonder if G, E, and L are collinear. No. JL is tangent to ABC. Are you sure about that? Right, let's see. Interesting. I did not realize that. That's good to know. Make it a segment instead of a line. So yeah, if we can show JL's tangent to both circles, then that would help. Yeah, GeoGebra helps a lot. Okay, so yeah, first of all, can we show GIHL is cyclic? So angle GIH, can we calculate that? So angle GIH. Why is the H the center of the mixtilinear incircle? It's because AEHF is like cyclic by definition. So these are both perpendicular by symmetry. So yeah, this is like the well-known idea of how you construct the mixtilinear in center. You draw the perpendicular to AI, then you draw the perpendiculars to E and F through the sides, and they meet at the center of the mixtilinear incircle. So yeah, I have the proof of that. I have it on yeah, I have a video on my channel. If you go back, it's around like 50 something or 60 something. I do a video proving that. Let's see what else we know. Are those collinear? Maybe L, P, and A are collinear. Looks like it. So that oh, and it looks like these are also collinear, right? Or these are also concurrent. We haven't proven it, but it's an interesting fact. And I wonder if DQ is perpendicular to EF. Whoops. Oh, this is the. So it looks like DR is perpendicular to EF. Yes. And parallel to AI. So yeah, a couple things going on, and I haven't proven most of them. These 2 circles are going to be tangent. It almost looks like these concur. I guess that's obvious. Well, so Is that obvious? Do they actually concur? Now I wonder if that's actually, no, they don't. It was a trick. Okay. All right. So we could try to show there's a homothency between these two circles. So I wonder, for example, maybe LJ meets AG. It's just a guess. That looks true. LJ and AG look like they meet at a point on the circle. So yeah, we're gonna have to figure out what the order is to prove all this stuff. Right now we're just finding a bunch of stuff. And maybe GP and H are collinear. I don't know if that's true, but it's possible. Wow, there is a lot in this figure. So it looks like GP and H are collinear. It's crazy. Yeah. Okay, so Geogebra is awesome. I think that's the lesson to either awesome or terrible, depending on how you look at it. Okay, so
AGL is 90, right?
A what L?
AGL.
Is more awesome than terrible. ABL or sorry.
J.
Oh, AJL. Okay. Let's see. I don't think so. I think it's close, but no. Interesting. So you're not against using GeoGebra. I like that. Okay. LD, it's well known it passes through the parallel from A to BC. I don't know if that'll be helpful. Okay, so can we do some homothency at L that takes one thing? So we can try to show a homothency at L takes triangle JPL to QSL. That would be one way to solve the problem. Let's see if there's any other lines that would work. Like we could try drawing in some of these points. I wonder if is LB perpendicular to AG? That might be obvious. Let's see. I don't know if that's obvious or not. No, it's not true. Okay. Is LB parallel to HG? No. All right, let's see. So we want to show PJ is parallel to QS. Maybe SQ is tangent to the Mixtilinear circle. It looks like it is. I don't think there's another intersection point there. So I think SQ is tangent. Let's check that. Yes. So P lies on the polar of S, so S would lie on the polar. So these should be collinear. And not only that, P would be the orthocenter of ASH, and this point lies on that circle. So we are learning quite a bit here. So SH is a diameter of this circle. So GIH. Yeah, so the circle GIH is really this circle. And is it obvious it passes through L? I feel like if I knew more properties of mixtilinear and circles, it might be obvious, but I think if we know it's tangent, then it's obvious. Yeah, if we know this is tangent to both circles, it's obvious. Then this circle right here, what do we know about this? Is DJ a diameter of it? I don't think DJ is a diameter. Let me just check. Yeah, because then D, H, and L would be collinear if that was true. So yeah, S lies on the polar of A, so A lies on the polar of S, and so that's why SQ is going to be tangent. And then we want to show that PJ is parallel to SQ. Or we could try to show angle LJP, like, because SQL is isosceles, because SQ and SL are tangents. So that kind of means that JPL would be isosceles. I don't know if we can try to show that. What?
Sorry, I accidentally entered it.
Okay. So that means that in triangle, an angle PDL, this is an angle bisector. I think that's right. Let me check that. Yeah. So we want to show that BC bisects angle PDL. I wonder if this quadrilateral is harmonic. So let's check it the other way. I don't think it is. No. I feel like I should have started with this problem. Yeah. Serdar, I feel like would have been interested in it. So yeah, maybe we can use projective geometry, right? We want to show BC bisects this angle. We could project DI, DP, DB, DL onto something, and we want to show that's harmonic. And maybe is that obvious? What do we project it onto? Do we project it onto AL? So or EF. Maybe EF is easier. Let's see. Yeah, I feel like there should be a way to project it somewhere. Are N, Q, and O collinear? No. So, yeah, what if I project it? Yeah, it doesn't seem like it should be that hard to show that this is harmonic. I just can't think of it right now. So we have this and this. We want to show that. Yeah, I just don't know where DL would intersect it at, but we want to show that those points are harmonic. Sam? Who's Sam? Oh, I am. Yeah. So I'll tell you what we know. So this circle, I think we can show everything about this circle. That S, G, Q, I, H, and L are all at least S, G, Q, I, and H. I think we can prove all lie on a circle. I think L also. I think we can prove everything here. So yeah, so then I'm just trying to show this circle of mothity. So I don't know that L, P, K, and J and D are cyclic. I'm still trying to prove that. And maybe so yeah, QELF is harmonic. We have a couple harmonic quadrilaterals. Yeah, T is the midpoint of QL. We have a lot of information here. So yeah, with this circle, I think if we could show that BC bisects PDL, then that would show that these circles are homothetic. That doesn't seem like it should be that hard. I just don't know the proof. what do you project onto? You could try projecting onto AL. So like, for example, if I let DI intersect AL at a point, and I want to show that that point P, this point in L, are harmonic, and where would I project those through? Let's draw this. Well, we know that this passes through this point. In fact, we could really calculate this angle. It's the average of arcs BL and UC, which is the average of. So this angle right here is really half of arc ABL, which is angle C. So yeah, it should be angle C right here. Is that right? I think that's right. So if I go like this, is that really angle C? No, I don't think so. No, it's angle ACL. Yeah. So this angle is angle ACL right here, and then this angle we need to show is also angle ACL. Maybe there's some similar triangles. So this is tangent. Maybe triangle PDB is similar to triangle ACL. That be? I don't know about that. Let's check it. Maybe it's true. Whoops. So that's 42.04. And this looks a little bigger than that, but let's check it. Yeah, so they're not similar. PDB, maybe it's similar to some other triangle. Let's see, what was this angle again? This was 42.04. Maybe AP. I wonder if there's some cyclic quad here that we're missing. Maybe not. KGAL is harmonic. KGAL. So why is that harmonic? We have one tangent. How did you find out that's harmonic? Oh, okay. Oh, I forgot it. I must have hidden that tangent line. I don't know why I hid it. But that's important. So yeah, then it's harmonic by definition. Yeah, we know that's harmonic. So yeah, maybe we could project that. I agree. So KGAL is harmonic. So where can we project it through? Actually, yeah, we don't know yet JL is a tangent. That's true. So we don't really know it's harmonic. But let's see. So can we show JPL as isosceles in some other way? We can show it's isosceles, and that would show that those circles are tangent.
We cannot really use this harmonicity because K becomes harmonic if it's defined via JA.
Okay, so like K, if we know JL is tangent, if we know it's harmonic, then that proves JL is tangent, right?
Oh, okay. But K is defined via JA, right?
A is, or J.
The
J,
only definition of K is via JA.
yeah. So K is defined in terms of J and A. And
Yes, so K is defined such that this would be harmonic.
yeah, exactly. This point P is tricky. P is like the intersection of A, L, and E, F. You think you prove GLHI is cyclic?
Do you think MJ equal to MH?
Sorry, MJ and MH? What did you say? So PJ equals LJ. Oh, maybe you mean HM equals. Sorry, I'm not sure what. Say it one more time. All right, I'll check the chat. It's cyclic. Okay, so you can prove it's cyclic. Okay, so So if PTL and this intersection point of ID and AL are harmonic, then that means T would lie on the polar of that point. With respect to this circle. And that point would be really far away. Let me try something. Okay, I think it's also the same. Like maybe I should draw this point where this meets BC. Oh, actually, I think it's trivial that BC bisects this because, well, if we know it's tangent, then it's true because angle PDJ is angle PLJ, which is ALJ, which is ACL. And then I just mentioned that it's a well-known fact that ACL is like BDL because LD passes through. Okay. So I think once we show these are both cyclic, then I can show the circles are homothetic. And I think I can show this one is cyclic. So I think it remains to show that this is cyclic. So for showing this one is cyclic, we have that angle HIS is 90, and we have angle HGS is 90. For point Q, we showed that like S lies on the polar. So S lies on the polar of A, so A lies on the polar of S. And so that would mean that like HQS and HLS are 90. So I think I could show this is cyclic, but I would still need to show SL is tangent. But maybe I could define things the right way and then use power of a point. So like if we use the radical axis theorem on like this, and the Mixtilinear incircle, then AGEF and the tangent are collinear. So I think that proves that. Yeah, we can show by the radical axis theorem that SL is tangent. So I think all we have to do is show that this is cyclic, and then I think I've solved the problem. See what time it is. 10:05. All right. Okay, so DLJ is it well known that sorry, let me think about this. That I think it's well known that GBCL is harmonic. I think we proved that a whole bunch of times on the channel. So yeah, so we don't really need to worry about. We know the tangents at G and L and BC are collinear. Yeah, we've proven that a bunch of times. I don't remember it right now, but it's probably not that hard to prove. So yeah, GBCL. Is there something we can project through that would show that easily? We project through it. So that's the same as saying AGET is harmonic. Or GBCL, GEFT is harmonic. And yeah, and that's true if you project through P, because that's the same as saying that GEFT, AEFH is harmonic, and we know that. Okay, so AEFH is harmonic, then project through P, then you get GEFT is harmonic, and then you project through A, and you get GBCL is harmonic, and then that proves, yeah. So yeah, we just have to show that this is cyclic. And we know that this is an angle bisector, so if we could show, that JP equals JL, I think that would prove it's cyclic. Oh, it looks like J is the circumcenter of GPL. So maybe we could try to prove it that way. So yeah, because JG equals JL, and then we could try to use an angle chase to show that half of GJL so let's label the center of the big circle V. I could show both are tangent. I think all I need to show is that half of GJL plus GPL is 180. Basically, I want to show that I want to show that J is a circumcenter of GPL. And maybe that's, I don't know how hard that is. So yeah, I should probably write out everything in the order that I've proven it so far. So by the radical axis theorem, AG, EF, and the tangent at L meet at a point S. So yeah. So that's how you start out. I'm gonna just type it out. By the radical axis theorem, AG, EF, and the tangent to at L meet at a point S. That's step one. Then S lies on the polar of A, so A lies on the polar of S. And so A, Q, and L are collinear. Or I could just say it like this. S lies on the polar of A, lies on the polar of S. And that means that SQ is tangent to the Mixtilinear incircle. I'll give it a name. Capital omega. So we know that. And then we know that angle HGS is 90. We know that angle HLS is 90. We know that HIS is 90. And by symmetry, we know that HQS equals 90 because HQS equals HLS. And so that proves that this is cyclic. So I'm just going to write this out. Angle HGS equals HLS. Is equal to angle HIS equals 90. And that means that HIQ GSL is cyclic. This should be HLS. All right, so that's the next step. And then we need to show this is cyclic, but once we show it's cyclic, then I think I could solve the problem. So actually, now I'm not so sure I can. Oh no, even if I show that cyclic, I think I got confused. Let me check if P lies on some cyclic quadrilateral. So is that cyclic? PUDH? Looks, no, it's not. But I think maybe showing that J is the center of this can help solve the problem. Because because I want to show this is an angle bisector, And if J is the center of this circle, then because these are, well, yeah, I would want to show, are DP and DL both tangent to that circle? Actually, I don't think that's true. BAL and BCL are similar. Oh. BAL. Oh yeah, I think we actually proved that. So BAL and BCL are similar, but then angle PDL, and I show that's angle AL per 180. Can I show angle PDB is angle ACL? 2 square root of BC inversion. So I guess, are you saying it's well known? It's well known that BC bisects PDL. AL and AX are isogonal. So BAL and BCL similar is well known. But that I get. Oh, I showed this was the bisector. Now I remember how I did it. So I'm gonna write this up. So AEHF is harmonic, and then we project through P. Oh, that was to show GBCL is harmonic. So here's what I'm gonna do. So AEHF is harmonic. Projecting through P, then we find GETF is harmonic. And then if we project through A, then we get GBLC is harmonic. GBLC is harmonic. And then that means that the tangents at G and L and BC concur at a point J. At point J. So that answers that part of it. Let's see. Then that follows that JKDL is cyclic. Wait, how does it follow that JKDL is cyclic? Is it just power of a point or something? Oh yeah. Angle chasing. Is it also so JL squared? Oh no. Okay, angle chasing. So let me think about this angle chasing. So, oh, because JKL is ACL, which is JDL. Okay, so it's well known that BDL is similar to ACL. Okay, so JKL equals ACL. Which is BDL. Well known since BDL is similar to ACL. That's well known. And so JKVL is cyclic. And then can we show P lies on it? Or do we even need to show P lies on it? Because my idea, if we could show P lies on it, I think that would be helpful. Which is the same as showing that J is, if we could show J as the circumcenter of GPL, I think that would really finish the problem. Is that just an angle chase, or so AGH is 90, right? So yeah, so APG is 90 minus GAP. And we could probably angle chase that in terms of angle GJL. Okay, so we want to show 90 minus GAL. And then if you take 180 minus that, we want to show it's half. So we want to show angle GAL plus 90. I think I'm really close. Y projecting through AEHF implies. Okay, so it's two steps. We start with AEHF as harmonic. Then we project those 4 points through point P onto the circle AEHF. So E and F just get swapped, and A goes to T and H goes to G. So then we have GETF as harmonic. And once we get that GETF is harmonic, we project that. So we're projecting GETF through A, not AEHF through A. So if you take GET and F, yeah. So I think I'm close here. So 180 minus this is 180 minus 90 minus that, which is 90 plus this. So wait, this is weird. So I want to show this angle. I want to show GPA is half of GJL. And GPA is 90 minus GAL. I want to show that 90 minus GAL is half of GJL. Is that obvious? Because it's harmonic? I think it might be. Yeah, I think that's true just because it's harmonic. Okay. So So V is the center of this circle. Then GJL is 180 minus GVL, which is 180 minus GAL, which is 180 minus 90 minus GPA. Okay, so let me write this out. So GJL is 180 minus GVL, which is 180 minus half of GAL. And that is 180 minus 90 minus GPA over 2. Maybe I'll split this into a separate line. See if that worked. Yes. Which is 90 plus angle GPA over 2. Which is, I'll say this is 180 minus 90 plus GPL over 2. So which is 90 minus angle GPL over 2. Okay, so this proves that J is this, so since JG equals JL, this proves that J is the circumcenter of GPL. So JG equals JL implies J is the circumcenter of GPL. And then we're really close, because then we have JPL as isosceles and SQL as isosceles. So then they're homothetic, and that solves, I think that solves the problem. So we have JP equals JL and SQ equals SL, so they have to be homothetic. L. And that implies triangles JPL and JLP and SLQ are homothetic. Homothetic. And that implies those circles are tangent. I think that's right. Is there anything I'm missing here? Let's see. Oh, did I show P lies on this circle? Oh, because this is the circumcenter, I think it follows that P lies on the circle, because did I figure that out? Well, actually, we need to know this is an angle bisector. Yeah, I think there's still one more step. I need to show P lies on JKBL. And we know JL equals JP, but we don't know yet that, so we know J lies on the perpendicular bisector of PL, but we don't know that this is an angle bisector. And we would need to know that to show that. But maybe there's another way we can do this. So it's probably just an angle chase, because angle JPL is JLP, and we show that's JKL. So that proves P lies on it. So so this implies JPL JPL equals angle JLP, which we showed, but we already showed that's angle JLA, which is ACL, which is JKL. JKL, and that means that JDP lies on JDKL. That should be sufficient. So yeah, it's overlapping the diagram a little bit, but oh well. There we go. All right, sound good? Anyone have any questions? Thanks for bringing out this problem. This is a fun one. All right, so I'm going to move on to the next one. Was this like your solution, Stefan, at all, or was yours different?
It had some parts the same, like proving that L is on GIH. I also introduced point S.
Okay.
But the idea of point P, that is very different.
Okay.
I didn't do it like that. I actually, for the tangency part, I intersected IL with the circle, the little circle, and then proved we have two parallel lines, which was also an angle chase.
IL with the Mixtilinear circle or the
No, the circle DJK.
Oh,
So basically like a homotopy.
interesting. All right.
And yeah, I also used that BAL and DLC are similar.
Yeah.
But didn't use it directly like that. I used the fact that LD intersects circumcircle of ABC at a point which makes an isosceles trapezoid.
Yeah.
Those statements are basically the same, the similarity in that, but I use it in that form.
Mm-hmm.
And yeah.
Interesting. All right. I'll have to check it out after the session. Sounds interesting.
I posted my solution on AoPS. You can look at it if you want.
Yeah, I'll check it out there. All right, so let's move on to the next one. This looks like a long problem, but yeah, actually I don't know if it's that bad. So we have a triangle ABC and AD is the altitude. V is a point on the circumcircle.